In our previous lesson, we were able to come up with three equations of linear motion relating the different quantities that we use to describe motion in a straight line. Now we want to go a notch higher and look at a situation where an object has been projected vertically upward or even falls from some distance straight to the ground. So we want to look at freefall, and basically free fall is that kind of motion where an object moves vertically upwards or even downwards, where only gravitational force is the force that acts upon that object. Now, we are saying it is the type of motion where gravitational force is the only force acting on an object. Now, we said initially that we want to limit ourselves to the kind of motion that we call linear motion, and on this we want to assume that a body is moving in a straight line. And if a body is moving in a straight line and taking a particular direction, for example, then it means the kind of motion described by that particular body is actually a vector. Therefore, we have to consider the direction of motion. In our case here, we are saying that the body is moving upwards or even downwards. Upwards or even downwards. Then we have to consider another aspect of the motion, which is actually the velocity of the body. Now, when we were looking at effects of force, we said that a force can accelerate a body, and in our case here, when a body moves vertically downwards, we have gravitational force which is actually constant at 10 meters per second. So this particular force will have an effect of accelerating this body by 10 meters per second, and this kind of acceleration is what we call gravitational. So what we call gravitational acceleration. Gravitational acceleration. Now, we still have a few equations that we can relate to this kind of motion. Now that we appreciate that By virtue of gravitational force acting on the body, velocity increases as the body proceeds or advances downwards. Or advances downwards. Now, there are a few equations that we can use to describe this motion, and these equations are what we will call equations of free fall. Equations of free fall. And in these equations, remember we said that if we say a body is freely falling to the ground, it means that only gravitational force acts on the body. Now, we want to come up with about 3 equations of free fall, and they are going to be derived from equations of linear motion, equations of linear motion, equations of linear motion. In general, we have 3, and number 1, V is equal to U plus AT. Number 2, S is UT plus a half AT squared. And then number 3, we have V squared being equated to U squared plus 2AS. Now, we want to use these equations to derive equations of free fall, and we start with equations when a body moves downwards. When a body moves downwards, and we have to note that acceleration for this motion is G, that is gravitational acceleration. So, if we start with equation number 1, it gives the relationship between velocity, that is both initial and final, and both initial and final. Acceleration and the time taken. Now, we will note that in this case, we talk about V being equal to U plus GT. In our case, V is the final velocity, U gives us the initial velocity, G is the gravitational acceleration, and T is the time taken. So in this case, we have no height factor. We have no height factor. Now, we go to equation number 2. Equation 2 relates the height of fall, initial velocity, time, and gravitational acceleration. Here, our equation now becomes height is equal to ut plus a half gt squared, where h is the height of fall. Now, u is the initial velocity, t is the time taken, and g is the gravitational acceleration. Again, we are noting that final velocity is not accounted for. It is actually not accounted for in this equation. It is not accounted for in this particular equation. We shall look at a third and final equation, which relates. It actually gives the relationship between the height initial and final velocity gravitational acceleration with no time factor. It actually does not have time factor. Now, our third equation now will become v squared is equal to u squared plus 2gh plus 2g. The three equations become the three equations become v is u plus gt. The second equation h is ut plus a half gt squared. Number 3, v squared is equal to u squared plus 2gh. Now that is for a body that is moving vertically downwards. Now how about a body that is projected or thrown up from some point on the ground? Now upward. Motion. Now remember, we said that gravity is actually a force and it always acts downwards. Now if you project a body upwards, it goes against our vector. It goes against our vector. If this is, say, a ball, and you have projected it vertically upwards, it goes against gravity. And therefore, G is negative. G is negative because gravity in itself is a force. If you want to change the direction of a force, then automatically you negate its effect. You negate its effect. The equations, therefore, will become now from equations of free fall. That we have just looked at. Actually, we have said there are three. V is u plus gt. Number 2, h is ut plus a half gt squared. Then 3, v squared is equal to u squared plus 2gh. Now, these three equations will give us the equation of free fall when a body has been projected vertically upwards. Now, taking into consideration that G is now negative, therefore, equation 1 becomes V is equal to u minus gt. Again, it gives us the relationship between the velocity final, the initial velocity, gravitational acceleration, and time. Only that in this case, the direction of action of gravitational force has been reversed. Now, this one relates initial velocity final velocity gravitational acceleration and time taken. Again, you realize that the maximum height reached has not been captured here. Now, our equation number two also substituting for negative g, height in this case will become ut plus or minus a half gt squared. Again, the equation relates the maximum height it also accounts for initial velocity it looks into the time taken and gravitational acceleration. Now, our equation 2 does not account for the final velocity, although we can use any equation to come up with final velocity, but if you were to limit yourself to the second equation, then the final velocity has not been captured. Now, we have the last equation number 3. The last equation, we are going to call it equation number 3. And equation number 3 comes from the third equation of Freefall. Again, we note that we still have g. Therefore, we need to do something about g. Now, therefore, we take v squared to be equal to u squared minus 2gh minus 2gh minus because g is negative in our case here. Now, this is to mean that the equation relates the following. A is the final velocity. B is the initial velocity. we have the gravitational acceleration and we have the maximum height. We have the maximum height. Again, our equation 3 has no time factor. It has actually no time factor. Now, we now have our equations both for a body moving upwards and that one moving downwards. If we are talking about a body that has been projected downwards, you use those equations. And if you are talking about upward movement, then the equations to apply include 1, V is equal to U minus GT. Number 2, H is equal to UT minus a half GT squared. And finally, V squared is equal to U squared minus 2 GH minus 2 GH. Let us look at examples where we are going to apply those equations. Examples on applications. Of equations. Of free fall. Now, the question reads, a feather is dropped on the surface of the moon from a height of 1.40 meters. If the gravitational acceleration at the moon is 1.67, we are supposed to determine the time taken for the feather to drop to the surface. Now, we want to start by actually noting down what the question provides. We have one, the height. The height is actually 1.40 meters. Then we have the acceleration g, which is actually 1.67 meters per second. Then we have the initial velocity as 0 meters per second, and it's also worth noting that the feather is moving downwards. It's actually moving downwards. So we are required to get the time. Now, we go back to our equations of free fall, and we have noted that our feather is actually moving downwards. Therefore, we consider V is U plus GT. Then you have our height being equal to UT plus a half GT squared. Then we have number 3, V squared is equal to U squared plus 2 GH. Now, when we look at the first equation, much as it has the time factor, we don't have V. The question does not give us V. Therefore, the equation has two unknowns, and that one rules it out. That one rules equation 1 out. Again, we consider equation 2. We have the height from which the feather has been dropped. We have the initial velocity. We have the time is what we are looking for, but we have g. Therefore, the only unknown we have in this question is actually t. How about the third? The third equation requires us to relate v squared, which is the final velocity, and which has not been given. Then we want to look for time, which has not been accounted for in the third equation. Therefore, that leaves us with equation 2, which we are going to apply. So we use equation 2, which states that h is equal to ut plus a half gt squared. Let us now substitute for the values that we have in that equation. H is 1.40 meters. U is 0 meters per second. T is what we are looking for. Then plus a half. G has been given as 1.67. Then we have our T squared. And remember that T is actually what we are after. Now this term reduces to 0. So we are left with 1.40, which is equal to a half. We multiply by 1.67, then times T squared. We can get rid of the half by multiplying both sides by 2, so that now 2.8 is equal to 1.67 T squared. We want to get T, so we divide by 1.67, and again we divide by 1.67, which is going to give us 1.677. So our T squared is equal to that, but we are interested in the value of T ourselves. T squared is 1.677. We want to get the square root of that, and this gives us 1.29. Remember, it's time, therefore the units are actually seconds. Let us look at another example. Example 2. Now, a baseball is popped straight up into the air, straight up, into the air and has a hang-up time of 6.25 seconds. Then the question requires us to determine the height to which the ball rises before it reaches its peak. Before it reaches its peak, we want to get the time, we want to get the height to which the ball rises. And what we have been given, the height is what we are looking for. The time, we have been given the hang-up time. Hang-up time that is the time to move to the maximum height. To the maximum height and back. Time to get to the maximum height and back. And this is what we were given as 6.25 seconds, but ours is to look for t, which is the time to reach the maximum height. And if 6.25 seconds is the time needed to go to the maximum height and back to the ground, then t is going to be given by 6.25 divide by 2, so that now we get the time for one way. And that gives us a duration of 3.125 seconds. Now, the initial velocity has also been given as 0 meters per second. Now we go back and examine the equations that we have. Equation 1, v is ut plus a half, v is ut u plus at. Number 2, h is ut plus a half gt squared. And the third one, v squared is u squared plus 2hg. But most importantly, we ask ourselves, to which direction has the ball been projected? Is it moving upwards or downwards? And clearly from the question, the baseball has been popped straight up. Straight up. That is to mean that if the direction of motion is upwards, upwards means against the force of gravity. Therefore, our g's are negative. Our g's are very negative. Now, which of these equations are we going to use? Equation number 1 has no height factor, so we rule that one out. Equation number 2 has the height, the initial velocity which we have, the time and g, and all of them we have. Now that is on the surface of the earth, we take g to be 10 meters per second, or what we call 10 newtons per kg. It is one and the same. Now, how about equation 3? Equation 3 relates final velocity, which we don't have, to h, which we are looking for. And therefore, that gives us two unknowns, and we cannot work with that equation. So we are left with equation 2. Equation 2. So we say, using equation 2, which says h is ut minus a half gt squared. That is what we want to get. H is what we want, so we can substitute for the values that we have, and u is 0. Then t is 3.125 minus a half g, which is 10, and t, which is 3.125 squared. Now this term reduces to 0. Therefore, height becomes 48.83. It's a height, therefore the units are meters. But again, we had this negative sign, which we are supposed to carry downward there, and that one should show us that the direction is actually against the force of gravity. Now, we look at one more example. Example 3. A stone is dropped into a deep well and is hard to hit the water after 3.41 seconds. We are supposed to determine the depth of the well. We are supposed to determine the depth of the well. Again, let us look at what the question provides. And we have G as 10 meters per second. Height is what we are looking for. Time is 3.41 seconds. Initial velocity is 0 meters per second. Now, consider our equations once more. V is u plus gt, then h is equal to ut plus a half gt squared, plus, because the stone has actually been dropped, so the movement is actually downwards. Then the last one, v squared is equal to u squared plus 2gh. Now for the first equation, we could have t, we could also have g and u, but we don't have v, and again we don't have the height factor. Again, for the equation number 2, the height factor is there. We have u, we have t, and we have g. The third one requires us to substitute for v, which has not been given. Therefore, we resolve to settle on equation 2, and we say, using equation 2, and equation 2 is h, which is equal to ut plus a half gt squared. We want to substitute for the values that we have. H, which is our quantity of interest here, is equal to 0 into 3.41 plus a half multiplied by 10 and then by 3.41 squared. Now this term again reduces to 0, and now h becomes 58.14. It's a height, therefore the units are meters. Now, we have been able to look at equations of linear motion when we have vertical projections. Next time we meet, we will look at horizontal projection. Thank you.